Okay, so I'll start with the recording here. Fine. So, what do you understand by PDE? Are you guys aware about partial differential equations? What do you know about partial differential equations? Yes, please. Okay, you are aware about that. So, what's the difference between a partial differential equation and an ordinary differential equation? What is the difference between them?
In partial differential equation, we need to change the behavior of the particular function with respect to one or two change in one or two variable as compared to all the variables, like dependent all dependent variables.
Okay, so what is the difference between ODE and PDE over here is here you will have multiple independent variables. So what you said, observing or changing the behavior, that's basically taking the derivatives with respect to multiple independent variables. Okay. So here we are going to deal with, and of course we'll be looking at change in the behavior with respect to one variable at a time. Yes. Okay. So here you will have multiple independent variables to be considered. And when we talked about ODE, we had only one independent variable and one dependent. We could have multiple dependent variables, but then independent variable would be only one in case of ODE. But right now we're talking about PDE, so it has multiple independent variables. Okay, so general notations is what we look into first, and then we start with the classification. Okay, so when we talk about the general notations over here, we call it as a function of say x, y, z. We can have p, q, r, s, t, and so on equals to 0. Now let's understand over here. Here these two could be considered as the independent variable. Generally, most of your books will use x and y as the independent variable. Z would be used as a dependent variable. Some of the books would prefer u in place of z. So you might find u also coming into the picture. Okay. When we talk about small p, it's the partial derivative of the dependent variable with respect to x. Small q would be the partial derivative of the dependent variable with respect to y. Small r would be the double derivative of the dependent variable with respect to x. S would be the double derivative with respect to x first and y then, or it could be y first and x then. The answer would be the same in both the cases. Okay. And lastly, t would be the double derivative of the dependent variable twice with respect to y. So these are the general notations which we will come across throughout the syllabus here. Okay. And we have used these notations before also for finding maxima, minima of two variable functions and things like that. So the notations may not be something which is absolutely new. And I hope everyone knows how to calculate the partial derivatives of functions. Is that okay with everyone?
Yes.
Okay. So proceeding further, once we are familiar with the notations which we are going to use throughout, we may also come across the notation like zx, which means the partial derivative of z with respect to x, zy. You can have zxx for r, zxy, or zyx for s, and zy square for t. Okay, so this is also one of the ways of writing the same thing. Also, you will come across this notation capital D, which is used for deva by deva x, and capital D dash, which is used for deva by deva y. So these are the different notations which you will find in different books. The languages vary depending on the book, but yes, the only difference is on the notations. These are the different ways it will be represented to you. Okay. We will now be talking about the first order partial differential equation. Okay. I hope you have seen your syllabus, and the first unit consists of first order partial differential equations. So before I go to first order partial differential equation, I need to talk about the order and the degree of a partial differential equation. Similar to what we have done with ODE. So when we talk about the order of a PDE, it is the order of the highest derivative present. Or I would rather write the order of the highest partial derivative present in the equation. So if we have the equation of this form, say if I have delta square z by delta x square minus delta square z by delta x delta y delta cube z by delta y cube equal to say 3xyz. What do you say is the order of this particular equation? Yes, please. I couldn't hear you.
Order 1, third.
Is the order 1? If you're not audible,
Third, 3, 3.
order is 3. Order is 3. What is order? How many times did you differentiate? So there are 3 terms over here where derivatives are present. Total 4 terms, one on the right hand side. 3 terms with derivatives, right? The first term is the derivative taken twice. Second term is the derivative taken twice. Third term is the derivative taken 3 times. So the highest order of the partial derivative is 3. So the order of the partial differential equation over here would be 3. Is that okay with everyone? Is this clear? Okay. Moving further. Next comes the degree of the partial differential equation. When we talk about the degree of the partial differential equation, it's the power or the degree of the highest order partial derivative. Same as we did for ordinary differential equation. So if I look at the equation above, which we have just considered, what is the degree over here? Yes, the degree is 1. The degree will be considered as the power of this term. There is no power. So you take this as degree 1. Is this okay? Also, one more thing to note here is whenever you're calculating the degree, none of the powers should be in fractions. None of the powers should be in fractions. So let's look at another example here. Say delta square z by delta x square, the whole raised to 2 by 3 is equal to delta square z by delta y square, or let me take this as, okay, the whole raised to 1 by 2. Now, tell me what is the order of this particular equation? Yes, please. What's the order?
Three.
Order is 3. Very good. The order is the highest derivative present. So the highest partial derivative present is of order 3. So the order is 3. How do you calculate the degree? How do we calculate the degree? Yes, please. To calculate the degree, first and foremost, I need to remove all the fractional powers, right? Yes, I need to remove all the fractional powers. So if you observe, you have the denominators as 3 and 2. I'll raise the power to 6. I'll raise the power to 6 on both the sides. So once I do that, here I'll get power 4. And here I'll get power 3. Is that correct?
Yes.
And with that, my degree now becomes how much?
Degrees 3.
Correct. The degree is 3 now. I hope this is clear. Is this fine, everyone?
Yes.
Okay. Now, once you've understood the power, the degree, and the order, we now move to the first order PDE. The name itself suggests that this PDE, which we are going to deal with, is going to be the function of x. Okay, and your syllabus is restricted to 2 variables with 2 independent variables. Okay. So when we talk about this, it means my general form would be x, y, it could be z or u, whichever, and only p and q. I will not have r, s, and t. I hope this is clear why I will not have r, s, and t. Yes, please. Because r
Yes, ma'am,
is
because it is first.
correct. R, S, and T are second order derivatives, right? Whereas we are dealing with only and only first order derivative, and hence we will not have R, S, and T over here. Any general partial differential equation can have those, but then this partial differential equation, which is of first order, will not have R, S, and T. Okay? So I hope this thing is clear with all of you. Any difficulties? Okay. Let's proceed further to looking at the different types of first order PDE, and then our target is going to be to learn how to solve them. When we solve them, we are actually expected to find curves which will satisfy the given PDE. Okay. So to solve them, we should know the different types, and once we know the different types, based on the different types, we are expected to solve them. So there are 4 different types of first order PDE with 2 independent variables. The first type is called the linear PDE. Is called the linear PDE. Let's understand. There are rules. Rule number 1, it is going to be linear in P, Q, and Z. It would be linear in P, Q, and Z, which means the degree of P as well as Q as well as Z, all 3 would be 1. Okay. Also, the coefficients of P, Q, and Z are functions of X and Y only. Which means I cannot have Z coming over there. I cannot have Z coming over there. So let's look at the standard form. I might have a function of X and Y multiplied by small p. I can have another function of xy multiplied by small q, a function of xy multiplied by z, and just a function of xy which is independent, which could also be a constant. Here the functions of x and y could be constants as well. Okay, so these are examples of linear PDE. Observe everywhere the degree of p is 1, q is 1, z is 1, that is your condition number A. The coefficients are all only functions of x and y. Let's look at some examples of this category. So let's look at example number 1. Say y times p minus x times q is equal to x, y, z plus x. Is it satisfying both the conditions? Degree of p, q and z is 1. Also at the same time, if I look at the functions attached to small p, small q and small z, they're all only functions of x and y. Is this okay? Any doubts? Is this clear?
Yes, ma'am.
Okay. Let's look at one or two more examples. Say I have xp plus yq minus x plus y times z equals to x square y square. Will this be linear?
Yes, ma'am.
Okay. What about the squares on x and y?
No, ma'am. They are not linear.
Okay. Now let's understand the rule. The linearity or the degree 1 is to be checked only for p, q and z, not for anything else. Are you understanding? Your linearity is dependent only and only on the degree of p, q and z, not on the degrees of x and y. X and y can have degree 100,000, negative, whatever. But your linearity is dependent only on x, p, q and z. So even though I have a square, this is linear. This is linear. Any doubts? Did you get this? The
Yes,
linearity, the linearity is only for p, q and z. Okay? Not for x and y. So even if I have a x cube here and y raised to 100 here, it will still remain as linear. Because there is no restriction on the powers here, right? There is no restrictions on the power of x and y. The restriction is only on the powers of p, q and z. I hope this is clear with everyone. Now I'll take one last example and then I will want you guys to give me an example. Let's say y times ux plus x cube times uy is equal to xy. Is this linear? Your z is replaced over here by u. Your z is replaced over here by u. Is this linear?
Yes.
Good. What about the coefficient of z? Can I add a 0 z here? If I add a 0 z, it is still linear. And the coefficient is a function of x and y. I hope this is clear with everyone. Okay, not z, I'll add over here u because we are working on variable u here. Okay. Now you guys give me at least one example. Come on, I want 2 examples from you all. Give me 2 examples of linear. You can use z, you can use u. Yes, students, no examples?
One over 2 ux plus 3 uy is equals to 5 sin u.
1 over 2 ux plus 3 uy is equal to?
5 sin u.
Okay, that works. I hope no one has any doubts here. Okay, 5 sin u will not work. No. Sin u doesn't leave u linear. The linearity of u is lost. Correct, right? You can have 5 sin x times u you can have, you know. Because what happens with sin theta? You have the expansion, no? Sin u would become u minus u cube by 3 factorial, u raised to 5 by 5 factorial. It's not linear. I hope the doubt is clear. Yes, please. Okay. One more example. Come on. One more example. Yes, please. Not a very difficult task. One example of linear. No one?
Which was 2x
I couldn't hear you, Farheen.
2x plus 5y cubed is equal to plus y square z
5iq is equal to x plus y square z.
z.
Okay, fine, good. So I hope the linear part is clear with everyone. We will now
Yes,
move on. We will now move on to type 2, which is called the semi-linear. Which is called the semi-linear. The rules will keep changing a little over here and there. basically you will be reducing the conditions on your variables each time. Okay, so when I say semi-linear, the first thing, it is linear only in P and Q. It is linear only in P and Q, and you will have coefficients of P and Q are functions of x and y. Is this okay? The coefficients of P and Q are functions of x and y. So now your linearity condition on Z is lost. So if I look at, say, the first example which we have used before this, okay, I look at the first example which we have used before this. I'm going to take the same coefficients, a small change. This becomes semi-linear. Do you understand the difference? Z is not linear. Z is not linear. Any doubts? Here your standard form would be a function of x comma y multiplied by p plus another function of x comma y multiplied by small q is equal to another function of x, y and z together. So the right hand side here entirely becomes your r. I hope this is clear. Yes, students. Okay. Let's move on to one more example. Let's move on to another example. So the example which was given by you all before this, 1 by 2 times ux, 3 times uy was equal to 5 sin u, is a semi-linear. Is a semi-linear. Because the degree of u is not equal to 1. Is not equal to 1. This was semi-linear. I hope this is clear. Yes, please.
Yes.
Okay. Let's move on to the third type. Let's move on to the third type. The third type questions here are quasi-linear. Okay, before we move on to the third type, give me one or two examples of semi-linear on your own. Give me 2 examples of semi-linear. Yes, please. Give me 2 examples of semi-linear. Come on, little quick. I don't think it should take so much of time.
3p minus 7yq is equal to x square z square.
Okay, this is semi-linear, good. One more example.
X plus y in bracket and then l multiplied by p minus z square q is equals to xy.
Is this semi-linear?
No.
This is not semi-linear. This is not semi-linear. Anyone who can explain me why?
Ma'am, minus xyq is equal to z square.
Yes, your coefficient of q cannot be having a z. Your coefficients of p and q should have only x and y, right? So the minute I put x square here, it's a mistake. So I have to put xy here and maybe a z square this side. Is this fine? I hope this is clear with all of you.
Yes, ma'am.
Okay. Moving further to the next type, that's quasi-linear. It's just going to be linear in P and Q. No second condition. It's going to be linear in P and Q, which means I am free to use the coefficient with z. So I'll have a function of xyz multiplied by P, another function of xyz multiplied by Q, and a function of xyz on the right hand side also. So let's look at some examples here. So I could have x square z into P minus xq is equal to zq. Are you understanding? The example just given before this, which we took it as not semilinear, was actually quasi-linear. Correct? There is no restriction on the coefficients now. The coefficients can have x, y, z both. So the example which I gave before was quasi-linear, not semilinear. Any doubts? Give me examples now. Give me examples. Come on, you all try. You guys give it a try. Should not take so much time. Now you're familiar, right?
In a bracket, z plus x multiplied by p
Z plus x multiplied by p, okay?
minus yz cube
Okay,
is equals to xy.
okay. This is definitely quasi-linear. Okay. Anyone else?
xy is x square p minus x square q is equal to y cube.
Okay. Why is this not linear? Why is it quasi-linear?
Since there is no z function over there,
Can I put a zero there? Is it not satisfying all the conditions of linear?
It is linear.
It is linear, not quasi. What is the condition of linear? P, Q, and Z should be linear, means the degree should be 1, and all the coefficients should be only xy. So even if I combine the coefficients of Q, you have used Q on left hand side and right hand side. So if I combine them, I would get this as xy times qp plus negative q x square plus negative I times q is equal to 0z. This is linear, okay? This is not quasi-linear. To make it quasi-linear, I have to add a z somewhere. The function of z should be present as a coefficient of p and q. Is this understood?
yes, ma'am.
Right? So good. When you try and understand what you have actually understood, okay? And the last type which we have is of course the non-linear. So these are all linear. The last type is the non-linear. So the non-linear would be none of the above. Meaning it may not be even linear in P and Q. So let's look at the examples here. P square plus Q square equals to 1. It's not linear in P and Q. What about P multiplied by Q is equal to 1? Here the entire degree becomes 2. Okay? Because it's P multiplied by Q. And the coefficients of P and Q were never allowed to be multiplied, if you would have observed. The coefficients of P and Q were always only and only x, y, z. Means in quadrilinear it was x, y, z. Previously it was only x and y. We were never allowed to multiply the small p ever with small q. So when it comes to non-linear, they will get multiplied. I hope this is clear with everyone. Are the 4 types of partial differential equations clear? Type 1, they're linear in p, q and z, and coefficients of all 3. The coefficients of all 3, that is p as well as q as well as z, were all having only and only functions of x and y. Okay, that was your linear. I'll take you back to the definition again. So when we talk about linear, it's linear in p, q and z. Coefficients are only functions of x and y. Coming to the semi-linear, the z is dropped from the linear condition. You can have any power of z, but p and q should be linear and coefficients of p and q are allowed to be functions of x and y alone. When we talk about quasi-linear, p and q should be linear, but the functions can have a z now. And lastly, non-linear has no condition of linearity on p and q. So p and q can be non-linear. That's how you have 4 different types of first order PDE with 2 independent variables. Is this clear with everyone? Any doubts in the 4 different types here? Yes, please. If the 4 basic types are clear, we will move to the methods of solving them. Shall we do that?
Yes, ma'am.
Okay. Fine. So we'll now move to the methods of solving these. Your syllabus consists of methods, the method of characteristics, first thing, which is used to solve a semi-linear or a quasi-linear. Okay, so therefore you should know the types. It is used to solve the semi-linear or the quasi-linear. So the method name is method of characteristics. Now what does the method of characteristics do? Okay, this is used to solve the semi-linear or the quasi-linear. Now what does this method do here is, it will convert the PDE into the ODE and find the characteristic curves. It converts the PDE into the ODE and it finds the characteristic curves. Initially, you will get general solution, but the minute you apply the initial conditions, you will get the particular solution. Okay. Now, how to begin with this? To begin with this, you will use the characteristic equation. And before I start with that, first let me write down the standard form over here, which we are going to use. So we are going to use pxy times p, qxy times q is equal to a function of xyz, or, okay, this is which one? This is semilinear. This is semilinear, okay? Or I can have a function of xyz together multiplied with p, a function of xyz multiplied with q, and equal to a function of xyz. This is quasi-linear. This is quasi-linear. So either you have a semilinear or you have a quasi-linear. Your characteristic equation becomes now understand this is small d, which is a total derivative symbol and not the symbol of partial derivative. So as you see, it converts the PDE into ODE. So you'll have dx divided by p, whether it is semilinear or quasi-linear, both the cases. Dy divided by q, and you will have dz or du divided by r. All the three will be equal. Out of this, you will get three different equations. You are expected to solve any two equations and apply the initial value conditions to find the particular solution. Is this understood by everyone? Is this okay? Yes, please. Is the structure or the skeleton clear? First thing you need to remember is method of characteristics can be applied only and only to semilinear and quasi-linear. Okay, the method of characteristics can be applied only and only to semilinear or quasi-linear. The first form which I have written is of the semilinear, the second which I have written is of the quasi-linear. Both the cases you have P, Q, R. The characteristic equation is given by dx by capital T, dy by capital Q, and dz by capital R. Equating two of them at a time, you will get actually three combinations, dx and dy together, and dx and dz, and dy and dz. You are expected to solve any two combinations. Again, question to question, it will vary which ones to take. Okay. And once you choose those two combinations, you will have to solve them using the method of ODE, and that will give you, after applying the initial conditions, that will give you the particular solution. I hope this skeleton or the structure is clear with everyone. So with this, we begin with sums. Again, there will be there are many different types of questions here, somewhere around three types of questions here. Okay. Depending on the values of P, Q, and R, there are three different methods to tackle the characteristic equation. Okay. Today we are taking the simple-most method where you don't have to do much of work in the solving here. Okay. So let's take the equation. I have 5 times P plus 2 times Q is equal to 0 with the initial condition of z at 0, y is equal to sin y. Z at 0, y is equal to sin y. So let's understand how do we solve this particular question. Okay. Let's compare it to the standard form. If I compare it to the standard form, first and foremost, is this semi-linear or quasi-linear? Whichever way, what is the value of P, Q, and R? What is the value of P, Q, and R? Capital P, capital Q, and capital R. Yes, please.
Capital P is 5, Q is 2, R is
Very good. So P is 5, Q is 2, and R is 0. So the characteristic equation over here would be dx divided by P dy divided by q and dz divided by r, which in this case turns out to be dx divided by 5, dy divided by 2 and dz divided by 0. Now I'm expected to take any two combinations. Which two combinations to take? Ideally, you take one combination which is with x and y both, or which does not have z. Okay, that is one condition you take. And second one, observe the initial condition which term is 0. The x term is 0, so you take the z with x term. You take the z with x term. So I'll take x term and the z term. I hope this is clear. So this now turns out to be a variable separable form. Now once it is in the variable separable form, can I write this as 2 by 5 times dx is equal to dy, and over here I can write 0 times dx is equal to dz. Once I do that, I'll be integrating on both the sides. Left hand side becomes y equal to 2 by 5 times x plus c1, and the right hand side becomes z is equal to c2. Because integral of 0 is going to be 0, but then the constant term will always come. Any doubts?
Ma'am, in the second last step, 0 x is equals to 5 times dz, right?
But then I can have 0 divided by 5 also, right?
Correct. Yeah.
So 0 divided by 5 will become 0, no? So instead of dealing with numbers on both the sides, I've just kept it on one side. You can obviously deal with both the sides as well, no problem. I hope this is clear. Any doubts so far?
No.
We leave this as equation number 1, we leave this as equation number 2. We'll be now working on the initial conditions. So it is given to me that z at 0, y. Now this y is an arbitrary value, right? So let's fix its value. Say 0, some epsilon is equal to sine of epsilon. I'm using a fixed value of y. You can use any symbol. Epsilon is not compulsory. You can use y1 also. No problem. y2, yn, anything. Okay? But then let's understand we are doing it at a fixed value of y. So this is what is given to me. When I substitute this in equation number 1, what do I get? In place of y, I'll put epsilon. 2 by 5 times 0 is equal to c1. Okay? Sorry, not equal to. It will be plus c1. I'm substituting x as 0, y as epsilon, and z as sine epsilon. So this implies when x is 0, y is epsilon, z is equal to sine of epsilon. Okay, these are the values I'm substituting in equation 1 and 2. So equation 1 gives me c1 is epsilon, and this converts the first equation into y is equal to 2 by 5x plus epsilon. Okay. Now working on the second equation, in place of z, I'll have sine epsilon is equal to c2, which is directly the value of c2. And equation 2 now gets converted to z is equal to sine of epsilon. Now let's understand your final answer should be in the terms of x, y, and z, not in the terms of epsilon or any point. Okay. So let's observe from here. Can I claim epsilon is equal to y minus 2 by 5x? And if I do that, can I then substitute it over here and I get sine of y minus 2 by 5x? This is your required curve which satisfies the given PDE. So this is your required solution. Is the solution clear for all of you? Is the solution clear with all of you? Yes, please. Okay. I'll give you a homework question. I'll give you a homework question which will be similar to this, which you have to try on your own. And if you don't get the answer next lecture, you will let me know. Okay. So this is question number 2, which will be your homework question, and you'll have to try it on your own. Okay, the question goes like this. 5 times ux plus 2x times uy is equal to 0, and the initial condition is u at 0, y equals to sine y. Your expected answer over here should be u is equal to sine of y minus 2 by 5x. So I think it's exactly the same answer which you should get. Okay. So I want you guys to try, and we'll do one more last question before we stop for today. Is that okay? Yes, please. Okay. So let's look at this question. Ux plus 2x times uy is equal to 2 times xu. And your initial condition is ux comma 0 is equal to x squared. Fine. So let's begin with this question. Again, this one is semi-linear. Your values of p, q, and r. How much is p, how much is q, and how much is r? Yes, please. What's the value of p, q, and r? Come on.
1, 2x, and 2x.
1, 2x, and 2xu. I hope no one has any doubt. Is this okay?
Yes, ma'am.
Okay. So let's solve this. We'll now have dx upon p, dy upon q, and this time it will be du divided by r because the variable is u, not z. Okay. This is my characteristic equation. Okay, so let's solve this. Dx upon 1, dy upon 2x, and du divided by 2xu. Now again, I'm free to take any two conditions. As we discussed before, we'll pick up those two which have x and y and free of the dependent variable. So this will be my first equation. And second equation, I'll take the one with 0 term, that is y over here along with u. So dy by 2x with du by 2xu. I hope that's clear. Is this fine? Let's cross multiply. So I have 2x times dx is equal to dy, and the 2x gets cancelled. I have dy is equal to du by u. This is variable separable method of ODE. Okay. Let's integrate on both the sides. The integral on left hand side gives me x square. Right hand side gives me a y, and I can have a c1. The constant could be both the sides, no problem. Here I'll have y is equal to log u plus c2, which becomes, or let me add c2 on the y side itself. You can add it both the sides, okay? U is equal to e raised to c2 plus y, or u is equal to e raised to y multiplied by c3, where c3 is nothing but e raised to c2. Okay? Now, once you've got this, we'll work on the We'll work on the initial conditions. So let's work on the initial condition. The initial condition like before. Let me do a partition here. Okay. Again, like before, we'll fix it at one of the points. So epsilon comma 0 gives me epsilon square, which implies when x is epsilon, y is 0, so u would be epsilon square. These are the values that we will substitute in equation number 1 and equation number 2. So when I substitute these values in equation 1, x square becomes epsilon square, y is 0, and I have c1, so I got the value of c1. So equation 1 becomes x square is equal to y plus epsilon square. In equation 2, when I put u as epsilon square and c3 e raised to 0, it becomes c3 is again epsilon square, which means u is equal to epsilon square times e raised to y. Now the value of epsilon square from the first equation comes out to be x square minus y. Let me substitute it here. So I have x square minus y e raised to y. This is my required solution, which is free of arbitrary constants, and it's a function of u, x, and y alone. Did you understand this? Any doubts? Yes, students? Is this method of characteristics okay with you guys? We'll of course do more examples in the next lecture, but whatever we did today, was it clear?
Can you
Yes, ma'am.
explain, Missy, can you explain the right part on the right side once again?
The part on the right side of question number 3?
Yes.
Okay. We worked on the initial condition. So in the initial condition, instead of x, which is a variable, we put a point over there. Okay, so you can have x0, you can have x1, or I have used epsilon. Okay, so you have x becoming epsilon. So you have u of epsilon comma 0 is equal to epsilon square. Now this means my x when it is epsilon, y when it is 0, my u becomes epsilon square. That's what I have written here. Is this fine?
Yes.
Now this I'm going to substitute in equation 1. So in equation 1, I have left hand side which is x square. X square will become epsilon square is equal to 0 plus c1. So 0 plus c1, I've just written c1 directly. Correct? So now I have c1 is equal to epsilon square, and I put this value back in equation 1. So left hand side which is x square is equal to y plus, in place of c1 I have substituted epsilon square. I hope that's clear.
Yes.
Now we worked on equation 2. Equation 2 was u on the left hand side, which is nothing but epsilon square. C3 as it is, e raised to 0. So e raised to 0 is nothing but 1. So C3 is epsilon square. So you substitute the C3 value again back in equation 2. So equation 2 becomes u is equal to epsilon square e raised to y. Your target is to get an equation which is free from arbitrary variables, which has your dependent variable, independent variables. It could have constants but not arbitrary variables. Okay, C1, C2, C3 are arbitrary. Arbitrary meaning their values can change depending on the initial conditions which we put. So constants are fixed, but arbitrary variables, arbitrary constants keep changing. So I need to calculate the value of the epsilon square, which I need to remove. So epsilon square is nothing but x square minus y from the first equation, and I put it in the equation of u. And that gives me u is equal to x square minus y multiplied by e raised to y. I hope this is clear.
Yes. Yes.
Okay. Everyone else is also clear?
Yeah.
Fine. And along with this, I'll give you one example as a homework on this lines as well. I will want you guys to try that question as well. Let me just note down the question. Okay. So you have u times ux plus ut is equal to u, and the initial condition is x comma 0 is equal to 2x. Now be careful, the independent variables are x and t and not x and y. Okay. So your answer would be, expected answer is 2x e raised to t divided by 2 e raised to t plus 1. So give a try to these both homework questions, and next lecture we'll see if there are any doubts in this and proceed further with more examples, a different type of examples on, again, semilinear and quasi-linear with methods of characteristic. Is this okay?
Yes, ma'am.
Right?
Yeah.
So